Hello, welcome to this quick and sweet video about how neural networks learn. In this video, you will learn neural network basics only in 25 minutes. Really 25 minutes, promise. We will go through codes and figures together. I didn't use any slides. It's just like pair programming. By the way, in the rest of the video, I will abbreviate neural network as NN. In each section, we will dig a NN concept, grasp the mathematics behind, and run related numpy and Keras code. Let's get started. This figure shows a high-level overview of the NN learning process. Training data consists of two parts. Examples we will feed into the network and corresponding outputs here that we want to obtain, ground truth. The weights of the NN is initialized with some random small numbers. At the forward pass, we feed the inputs to the NN and calculate NN's output. Okay, then we need to compare the NN output and ground truth to understand if NN did well. Here, we calculate an error by comparing NN outputs to the ground truth. This is the end of forward pass. Backward pass is about updating the weights, and amount of update depends on the amount of the error. If the error is small, obviously NN learned well. If the error is big, of course we need to shift the weights more radically. After updating the weights, we make the next iteration with the updated weights. We iterate until we get a reasonably small error. Looking at the figure again, I see three chunks to be dissected. First chunk is calculating the NN output. Second part is the details of the error functions, and the third part is the backward pass. Biggest secret of the backward pass is calculating the update that we wanna do to the weights. All might sound a bit unclear, but we have the whole time to explore the details. First, we make the forward pass and calculate the NN output. We start easy to this part, so I generated linear data like this. We will try to teach NN the function 2x plus 3. I generated 20 points. I took the interval -1 to 1, put a tick each 0.1, makes 20 points. Then I generated a little perturbation, delta, with mp.random.uniform, as you guess, uniform random variables. Again, I picked an interval, then give how many points I want to generate as an argument. Here it is. I passed x.size, better than hand coding, 20 size of the variable x. This is the y, 2x plus 3 plus the little noise. Now, forget that we already know the linear nature of the data. In the absence of further information, we start with the simplest model possible, which is a linear model. So we assume NN will learn a linear function like this. Is this a good assumption? Most probably we will see how the model performs. We choose the variable names W and B for weight and bias, and usually you see these variable names in NN literature. Weights scale the input, bias is an additive constant. Aim of NN training is to approximate weight and bias based on the training data. When we run x's through the final model, we should get the y's. For this data, it's a linear curve fitting. Once more, we have a model with some unknown parameters, and we need to estimate these two parameters so that the error between predicted output and the real y's is as low as possible. We have an element missing here. We need a way to measure the error. Way of measuring error is called the loss function in NN literature. Loss should be low if the points are identical, high if we make a bad fitting. Hence our approximation process is to find V and B so that the loss is minimal. For fitting our model now, we will pick a quick loss function and revisit the loss functions later again. We will pick square difference. For each element of the two input vectors, this loss subtracts two elements, squares it, and we make a sum over all the elements. Finally, average. something like this. Here is an example. We take each point, calculate the diffs per element, square them, and scale by the input length. Okay, we have everything, so we can start making the first forward pass. Let's define our model. X is a numpy array. You see above, if you remember, B and B are numpy arrays as well, hence multiplication is just numpy operations here. Next, we define our loss function. Note that we are building an array of differences, afterwards taking the square element-wise, and finally producing a scalar by averaging over the array dimension. Once again, loss is always a scalar. We want to measure the difference between an end result and ground truth numerically. Now we can initialize the params and invoke the model. I initialize the weights as ones and B as zeros. Let's run input points X through the model and get the output Y hat. This is the result NN gives at this iteration. Next, we calculate the loss. We feed ground truth Y and freshly calculated Y hat to the loss function. Here is the loss value. Great, we made the first iteration. Before doing the next iteration, we need to update the weight and the bias. We want to optimize the loss, we want to minimize it, make it near zero. We will optimize the loss function with respect to the parameters using the gradient descent algorithm. In this section, we will build our intuition for how gradient descent works. Idea of gradient descent is just following the steepest slope. Imagine you are blindfolded in a rough terrain and your objective is to reach the lowest altitude. One of the simplest strategies you can use is to feel the ground in every direction. Take a step in the direction where the ground is descending the fastest. If you keep repeating this process, you might end up at a lake or even better, somewhere in a huge valley. Our rough terrain is our loss function. Minimizing the cost function is analogous to trying to reach lower altitudes. We are blindfolded, remember, since we don't have the luxury of evaluating the value of the function for every possible set of parameters. Feeling the slope of the terrain around us is analogous to calculating the gradient, and taking a step is analogous to one iteration of update to the parameters. More formally, gradient descent seeks to find the global minimum of a function. To do that, it calculates the gradient at an initial random point and moves to another point in the direction of descending gradient until it reaches a point where the gradient is zero. We start at this initial point. This line is the tangent line, and local minima should have a slope of zero, like this. Here is the local minima. At this point, we have two choices. Either move along this direction and pick this red point as the next point, or this direction, hence this point as the next point. This point doesn't help because tangent line doesn't flatten at all. We move a tiny bit along this direction, but just a bit. If we make two big steps, we can miss the local minima. For this reason, we usually use a tiny positive scalar called learning rate. We usually multiply the gradient at the point with the learning rate to make sure that the steps are small enough. You wouldn't want to do something like this whoop and end up here missing the local minima. Hence, we update the parameter v as the following. We compute the derivative of the loss function with respect to the weight, multiply it by the learning rate, then subtract it from the current weight. Same applies to the bias, like this one. So how do we compute d loss dv then? We move on to the next section. In order to compute the derivatives of the loss with respect to a parameter, weight or bias, we can apply the chain rule and compute the derivative of the loss with respect to y hat, because y hat is the input to the loss function, times derivative of the y hat with respect to the parameter, either weight or bias. Recall that our model is a linear function and our loss is a sum of squares. Let's figure out the expressions for the derivatives. Again, the expression for the loss. In order to get a derivative, I take the derivative of the squared expression, this one too, bring it down, put a minus to the top to make it 1. Finally means inside state the same, and finally mean here brings this term. Recalling the model, here is the model again. I differentiate the model with respect to w and x comes. I differentiate with respect to b and result is just 1 because the first term, this one doesn't have a b at all, it brings 0 and del b is just 1. Let's put it together to express the gradient. Gradient is the vector of partial derivatives. Letter nabla here is used for gradient in mathematics, and we put the variables to this corner, like this one, to make it explicit that partial derivatives are with respect to these two variables. Once more, here is the chain rule. In order to calculate d loss dv, we can chain d loss dy hat and then dy hat dv, similar for the bias parameter like here. If we write it programmatically, I just multiply the above functions that I defined. Notice the sums here. We are summing over all the data points to get a single scalar quantity for each partial derivative of the loss. Gradient is not only a list of derivatives, it has a geometric meaning too. Just like in one variable calculus, in multiple variable calculus, gradient points to the direction of maximum slope, like the uphill direction. Looks like we have everything we need. Model output from the forward pass and derivatives to make the backward pass. Starting from random values for parameters w and b, again, we will iteratively update the parameters. In real NN setups, the number of iterations is usually until loss becomes reasonably slow. This time we will do a fixed number of iterations. Number of iterations in NN terminology is called epochs. An epoch means one pass over the whole training data, and during this pass we update the parameters. Before starting the iteration, this is the params w and b again. Training set of 20 points of each x and y are here too. Once more, the function we wanna learn is 2x plus 3. Remember, this is the training loop. Here, these two lines are the forward pass. We calculate the model output and the loss between the ground truth and the model output. Then we calculate the gradient. Remember, gradient has 2 dimensions because there are 2 variables. First dimension gives us the rate of change in w, so we update w with LR times rate of change in w. For each epoch, and same for b here. For each epoch, I printed the epoch number and the loss value. We iterated for 200 epochs and I pick learning rate to be this number. A small enough value. Oopsie. I forgot to click train. And also gradient. Okay, I will just click them again. And also I need d loss. Okay. Then it should function. Here is the result of the iterations. Loss starts 9-ish, 8-ish, and goes down to 8, 7, 6, 5, 4, 2, 1, then just below 1, 0.5, 3, 2, 1, and this number. And then goes through, 0 points. This loss is quite fine, very close to 0. Result of updates is this W and B. Function was 2x plus 3. Again, W is close to 2 really, and B is quite close to 3. So I would say this is a good learning result. So far, we had a look for mechanics of training one layer network to approximate a linear function. We focused on a quite simple regression problem that approximates a linear function with only one input and one output. By starting with an easy function, we were able to dig the mechanics of the model. Differentiating the loss function was easy, differentiating a linear model was easy. If we go back to the first diagram here, the exact details of the forward and backward computations are not really needed to understand the training procedure. We run the input through the model, we calculate the loss, we calculate the gradient of loss with respect to the params, updated the params by the amount of the gradient. This is a very generic process. Loss can be in another form, number of params can be more, and model can have more layers, hence be a more complicated model. In this section, we make some changes to our model architecture. We will implement a multi-layer network to approximate a quadratic function. For this purpose, we will get help from Keras neurons. A neural network, as the name suggests, is a network, like this. And the building blocks, the nodes, are called neurons. Inputs of a middle layer neuron is the outputs of the previous layer's neurons, like this. Here is the input, and here are the outputs. A neuron is a linear transformation of the input, multiplying the input by weight and adding a bias, followed by a fixed nonlinear function called an activation function. Mathematically, we can write an expression for a neuron like this. Again, x is the input, w is the weight, the scaling factor, and b is the bias, an additive constant. F is the activation function. We can pick it from a huge variety of functions. Here, inside the parentheses, there is a linear transformation going on. Activation functions bring the non-linearity. Non-linearity is a quite good thing if we need to approximate non-linear functions. We have another video dedicated to activation functions only. Again, what is a NN? Looking at the figure, again, we see that NN is just a composition of functions because we feed outputs of a layer as an input to the layer, next layer, like this and like this. Then we can write the composition just like this. Hope picture is clear. Now we can get started with Keras neurons and see how they operate. First we make the imports. I will import dense layer. Dense is maybe the most widely used Keras layer. It is the regular, deeply connected neural network layer. In this picture, it's exactly this layer, or this layer. It has a fully connected inputs and outputs. Let's look at the dear dense. It's just, neural network stuff. I see it. Let's create a dense layer. First of all, we need to tell the output size of the layer. I will give 2. This param is also called units, and this is a quite important parameter. Output shape should be the shape of whatever you want to compute. Second parameter is the input shape. Obviously, you need to tell the dense layer the shape of your input. Input of dense layer should be a 2D vector. First dimension is called batch, and the second shape is the input size. None is the batch size here, and I will feed the inputs of size 3. Here is what we want to do basically. Like this one, we want to transform an input of shape 3 to output of shape 2. Forget batch for now. Let's do the computation first, then shapes will make sense, I promise. Units is again output shapes. I will make a 1 to 3 numpy array and call it x. Shape is 1 to 3. We promise to the dense that input size will be 3. I will run the input through the layer. Here is the result. Shape is 1 to 2, as promised. Skip the dimension 1, second dimension is 2. Think about the matrix multiplication. In order to create a two-size output, the weight should be 2 to 3 shape, just like this. Here it is, 2 to 3. If you don't believe me, look at the dense layers weights. If we sketch the matrix multiplication, it's even easier to see. Here, second dimension of the first matrix should match to the first dimensions of the second matrix. Because multiplication happens as WOP, WOP, and WOP, WOP, the result is the first dimension of the first matrix times second dimension of the second matrix. If you look at this transformation, indeed, dense layer doesn't have to know the first dimension of the input in order to allocate space for the weight matrix and initialize it. Again, first dimension of the matrix, weight matrix, is the input size, and the second one is the output size. Weights are initialized randomly, by the way, because we didn't do any updates yet. Also, activation function is linear function by default, because we didn't specify anything yet. Okay, now we try a bit different input. x2 will have size 2 to 3. Dense will say yes to this input because remember we made an agreement that second dimension of the input shall be 3. Let's run it. Here is the resulting shapes, 2 to 2. Once again, weights is 2 to 3. Here it is. So 2 to 3 and 3 to 2 matrices result in 2 times 2 to 2 matrix. Here is the picture. Again, multiplication this time is this row, wop, wop, hop, and wop, 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 wop. Result has an extra row now, this one, because input has an extra row. Now what can be a batch here? If we compare two inputs, this one and this one, they don't look so different indeed. This input is two chunks of rows 3 and the first input is one chunk of 3 size row. So row size is fixed, it's 3. But we can put more rows as we want. Number of chunks is called batch basically. Visiting the dense again, let me find it. Here it is. We set batch size as none because there can be any number of batches. It doesn't matter for the weight size. However, we need to tell 3 the row size, otherwise dense cannot form a weight matrix at all, and same for the output size too. If you have a 2000 training samples, you can make batches of 5, 10, 20, 40, 50, 100, 200. It depends on how many matches can you fit into the memory, because as you see, matrix multiplication is operated on the batch level, not on the individual samples. Hope batch business is clear now. Now a size mismatch comes. Here is an input called y and the shape is 3. Second dimension is not here. Let's run it. Oopsie-doo, there is a huge shape mismatch because input is not two-dimensional at all. It's only one-dimensional. Remedy is reshaping this input. This reshape is still a no because shapes doesn't match. Here there are 3 batches of size 1 each. Remember, dense wants a row size of 3. Now comes the correct one. Okay, great. We understood the basics of one layer. Now we can put 2 layers on top of each other to make a 2-layer NN. Here are 2 dense layers. First layer is our friend dense. I copy and pasted. Second one will take the input of the first one. Hence, its input size matches the output size of the first dense. Here is the first output. Okay, first inputs. Here is the first output. Then I will run this output as input to the second layer. And then the second output. Final result is of size 5 because we ask 5 as the final result. Great, we can make multi-layer Keras networks now. Next object is shaping our output according to our needs. Sometimes we want to output probabilities, sometimes we want to output some values. Also, we need to tell the NN how we want to compare the ground truth and the results. We have another dedicated video for these subjects, activation functions and loss functions. For this video, this is the end because we covered mechanics of learning. Hope content was useful. In order to understand fancier layers such as convolutions and sequential layers, I think it's good practice to dig really basic layers, especially the input and output shapes. See you at the next video. Until then, stay safe, happy and tuned. Bye bye.